Alright, welcome back. We'll continue to discuss shear stress and shear strain. Now we will solve this specific example. So here you can see the problem. A bearing pad of the kind used to support machines and bridge girder consists of a linearly elastic material capped by a steel plate. So here this is a specific example, the figure of the example. Rubber elastomer and the top is steel plate. Assume that the thickness of the elastomer is H. So this is elastomer R, rubber, and the top should be steel S. So the thickness of the rubber H. And the dimension of the plate are A cross B. And the pad is subjected to horizontal shear force V. In this case, you have to obtain the formulas for the average shear stress, tau average in the elastomer, and the horizontal displacement D. So this you can find the displacement D. Alright, then using this specific example, let's try to solve this example. Okay, by using the specific equation of the shear stress, we can define tau is equal to V over A, right? And we know that the cross-section area of the plate is the cross product AB, right? AB. So this should be the final form of tau we can use to develop the strain component and the displacement D, right? And what about gamma? The shear strain gamma can be defined tau over G, and we just defined tau is what? Tau is equal to V over AB, right? And eventually we can simplify it as a V over A, B, G. So this is what? This is shear strain gamma. And with very small gamma, by considering very small shear strain gamma, we can define that here. I would like to highlight the D and H, right? Right, zoomed in, and here this should be D and this is H. DH. Using this specific geometric condition, we can define D over H equal to tangent gamma. And gamma we just define as a V over EG. Right? So in this case, we can define that D is equal to H tangent VABG. And we know that the tangent ABG, tangent VABG is equal to V over VG in case of very small deformation, right? So using this specific relation, we can define that D is equal to H gamma, and this should be AB over ABG. So using the geometrical condition of this deformation, we can define the shear stress, and after that we can define the shear strain, and using the specific geometric condition with very small gamma, we can identify the tangent gamma is equal to D over H, and eventually we can define the total deformation right? The total displacement, horizontal displacement, D as V over AVG. So, again, the concept of very small deformation, very small gamma is important. Okay. Now move on to the allowable stress and allowable loading condition, allowable load. So as a mechanical engineer, we are mechanical engineer, right? So we do engineering design. So in this context, solid mechanics can provide the basic knowledge to perform the design of all objects, such as component and system or mechanical structure. And to perform the proper engineering design using material, the engineer needs to properly understand the strengths of material, how the strengths applied on the certain material. So understanding the strength is very important. So here, what is the strength? Strength is the capacity of the object to support or transmit the load. That is the definition of strength. Okay. And for successful structural design, the actual strength must exceed the required strength. Okay. So that is the kind of some concept of factor of safety. So here, the factor of safety using the concept, we can define that. The factor of safety is equal to actual strength over required strength. So, using this basic definition, we can build durable and robust mechanical structure, and to avoid the failure of the total system, the factor of safety should be higher than 1. And the margin of using this specific concept to avoid the failure, the factor of safety should be larger than 1, right? So the margin of safety can be identified. Margin of safety is n-1. That is the margin of safety. And this should be larger than 0. Okay. Now, let's try to discuss allowable stresses and allowable loading, the specific definition. So allowable stress is we can define by using this specification. Allowable can be identified as is over factor of safety. So, in case of tension, we can define the allowable normal stress is equal to yield stress over factor of safety n. And in case of the shear stress, the allowable shear stress is equal to yield shear stress over factor of safety n. And basically, yielding begins when the yield stress reaches to any point within the structure. So once the stress reaches to the yielding condition, yield stress, the entire structure the yielding status begin. Okay, so certain part reach to the yield condition, then entire structure have to be considered the yielding behavior. And for brittle materials, the ultimate stress we write down as a UTS. Ultimate stress can be used instead of the yield stress, because you know that basically the brittle material we cannot find the specific yielding point. So the ultimate stress can be used instead of the yield stress in case of the brittle material. Alright. Then now, by considering specific area condition, we can define allowable loading condition. So with the determining proper definition of area, it is possible to identify the allowable load on various force conditions. Basically, the allowable load is equal to the product of allowable stress and area. So this is the basic equation. Again, product of allowable stress and specific area. So again, by properly determining the definition of area, we can define the specific allowable loading condition. In case of the tension and compression, the net area should be considered to define allowable stress. So in this case, P allowable loading condition is equal to sigma allow multiplied by the net area. And in case of this tension and compression, the net area can be specified the value of the gross cross-section area minus the void area. And about the direct shear, in this case we have to consider cross-sectional area. So the allowable loading condition in direct shear condition, you can identify P allow is equal to tau allowable multiplied by cross-section area. And in this case, the cross-section area, the area over which the shear stresses act. And one another important allowable loading condition we can define at the bearing condition. So in this case, the allowable loading condition can be identified the product of bearing stress sigma B and the cross-section area of bearing area, which is projected area. We call this is bearing area, and the bearing area can be defined. I'd like to write down here the projection of the actual contact area So I would like to give you the specific example about the bearing area. Actually, the definition is that the projection of the actual contact area. So here, there is the mechanical structure. The hanger is fixed by the clip angle by the specific bolt. Alright, so this board. This is object A, hanger, and this is object B, the clip angle. So in this case, we can define the diameter of board and the thickness of the thickness of the clip angle T. So in this specific structure, mechanical structure, we can define the ball bearing area as the board diameter times the thickness of the clip angle. The board diameter D, right? This is what? Board diameter, and again the thickness of the clip T can define here. So the board diameter times the thickness of the clip angle, in this case bearing area, right? Then using this specific condition, we can identify each different allowable loading condition. Okay, then let's move on to the next concept, design for axial load and direct shear. From an engineering perspective, the meaning of design is that here, the design, the determination of structural properties in order for the structure to support given load and perform its intended function. So that is the kind of some definition of design in case of the engineering perspective. To properly design mechanically durable structure and mechanically robust structure, we need to follow this specific relation: simple tension and compression. So required area, in this case, required area can be identified as a load to be transmitted over allowable stress. So this can be simplified that the required area equal to what? Transmitted loading condition over allowable stress. Sometimes it can be shear stress and sometimes it can be normal stress, but now I use just the normal stress to highlight it. So using this, we can specifically define allowable normal stress as over required area. So as I told you in previous slide, to properly define the loading and stress condition, we have to consider each specific the definition of area. So that should be the required area for each specific the transmitted loading condition. So using these two specific it's that if we know the transmitted force condition and required area, we can define the allowable stress. And if we know the transmitted loading condition and allowable stress, then we can define the required area. So if we can define two or three of them, we can properly design certain mechanically durable and mechanically robust structure. All right. Then I would like to stop here, and we'll continue to solve the specific example next video clip.